Another very useful and important principle that shows up a lot in signal processing, and especially here in adaptive filters, is that of orthogonality. We can see this actually pretty easily by starting with the Wiener equation, which is also called the normal equation, meaning that something is normal or orthogonal to a surface. So the reason for the other name of this. So we start with this Wiener equation, and we're going to expand it back out into the terms that it originally represented, which were these expectations of y y transpose, I'll just do that, times w opt is equal to expected value of yd. I actually went ahead and added back in the notation for complex systems. I've been a little bit inconsistent there. It's because we usually have real systems, but whenever possible I'll try to put in the complex notation in case that's where you're at. Also, I noticed I left out the n indices just for brevity. A few other things to note. This, of course, is a column vector, as y is a column vector. And we have a matrix, and this is a column vector. So a matrix times a column vector is going to give us a column vector as well at the output. So I'm going to do something just to make this a little bit easier going forward. I'm going to take the Hermitian transpose of both sides of this equation. It shouldn't change the equality, but it does put it into a form that's a little bit easier for the next steps. Now recall that the expectation is a linear operator, so we can move the right side of this equation over to the left and throw all the expected values within a single expectation. In other words, we're going to have w opt h now times the expected value, and we'll have yy minus dy as such is equal to 0. Now we can factor out the y Hermitian over on the right, and I'm also going to now actually I've made a slight mistake here. Let's fix that. That is that w opt, we're going to have to put that inside the expectation. There we go. Now we'll factor out the yh, giving us this nice expression. And recall that this is actually our optimal d hat estimate. So, and now we have d hat minus d, that is our error, e. So based on that, we can come over here and write that the expected value of e times our input vector is equal to 0. I should note, and probably make these bold, these are 0 vectors. And what we have over here is a row vector, but that's okay. In essence, this is telling us that under expectations, the error is orthogonal to the input, to our observation. Another way of looking at this is if our input is 0 mean, then the error and our input are uncorrelated. I like to think of it as we have extracted all the information we have available to us from the input in trying to minimize the error. And anything that's left of the error cannot be predicted or has no correlation with anything in the input. Now is probably a good time to talk a little bit about orthogonality with respect to random variables. We've run into this concept before in vector spaces with inner products. It turns out that the set of random variables with zero mean and finite variance forms a vector space. Now, in order for us to go beyond that, to talk about orthogonality and such, we actually need an inner product or Hilbert space. So in order to have an inner product space, we need to have an inner product. So let's look at the properties of an inner product to put context on what we're talking about. The first is symmetry. That is, the inner product of x with y is equal to the conjugate of the inner product of y with x. Of course, if they're real, that conjugate goes away. The second is linearity. And this is similar to the linearity we've seen with, say, expectations. And that's where we're going with this, that x plus by is comma z can be factored out just as you would, say, with a regular, say, sums and product operations in parentheses. The next is positive definiteness. That is, that the inner product of x with itself is always going to be positive unless x itself is 0. Okay, based on that, let's go back and revisit what we have with expectations. These things should show up. We would expect to see the same type of thing, and indeed we do. For expectations, we have linearity, we have positive definiteness. Remember that the expectation of x with x is the variance. So as long as we do not have the trivial thing, such as a constant, we're going to have x, or we'll have positive definiteness. And the symmetry, the expectation is the covariance. So if we define it as the expectation of x y star, or y conjugate, is equal to x comma y, we have a valid inner product, therefore a valid Hilbert space, and we can now talk about orthogonality, and a lot of the linear algebra that we've used in the past can be brought to bear on expectations.